chapter. Okay, first one, let us know what is the meaning of periodic motion. Write the heading: periodic motion. Periodic motion. Look here, the word itself says periodic motion, which is happening in a fixed period of time. For example, spinning of earth. Every 24 hours, that spin is completing. Periodic motion. Revolution of earth around the sun, 365 days. Periodic motion. Movement of a pendulum. Say, for example, if I am just pushing this pendulum, it comes to this point, come back, go to other side, like that. So this is periodic motion. It happens in fixed interval of time. So these kind of motion, which is repeatedly happening in a fixed interval of time, is known as periodic motion. Write down. If a motion is repeated again and again, if a motion is repeated again and again, if a motion is repeated again and again, after an interval of time, after an interval of time, after an interval of time, the motion, if the motion is repeated again and again within a fixed interval of time, that's correct, within a fixed interval of time, within a fixed interval of time.
Sir, can you repeat it again?
If a motion is repeated again and again within a fixed interval of time, this motion is called periodic motion. Example.
Sir, you gave these notes?
I gave the notes, but we will go in detail. That's what I'm telling you.
Okay, sir.
Notes I gave you in case you miss some class, or if you are unable to hear what I'm speaking, you can check the note and write. But when you write and learn, you will learn it. This is a pattern we were following before. Due to lack of time, one unit I went a bit faster. That I will repeat.
Yes,
I told
sir.
you. Oh. Okay.
What is the last motion? It's called periodic.
Is called this motion is called periodic motion. Example: spinning of earth, spinning of earth, revolution of earth around the sun, revolution of earth around the sun.
Sir, are these examples?
These are example. Oscillating pendulum, oscillating pendulum. All these are happening in a fixed interval of time repeatedly. Any other example you can put forward? Rotation of a fan. Okay. All these are examples of periodic motion. Any doubt?
No, sir.
No, sir.
Continue.
No, sir.
Next one, oscillatory motion. Oscillatory motion or vibratory motion. Oscillatory motion or vibratory motion. Oscillatory motion or vibratory motion. Look here. A pendulum which is first going to one side and coming back, again going back, again coming back. What is the specialty of this motion? Look here. First to and fro, going forward and coming back. To and fro, back and forth. These are the two segments of the motion. Look here again, I'm telling you. Pendulum first go here to, coming back, fro. Then back and forth. 4 segment. It happens in a fixed interval of time. A spring. If you just pull this spring and leave it, this spring will go up and down with respect to mean position. So to and fro, back and forth, happening in a fixed interval of time. So they go along the same path repeatedly. But if you take a spinning of the earth, it keep on going in the same path. It will not come back. After 24 hours, do you think earth will spin back? No. Keep on one side. So periodic motion means both are periodic motion. This is periodic motion. This is periodic motion. Spinning of earth, oscillation of pendulums, both are periodic motion. But motion of similar pendulum is which one? Vibratory motion or oscillatory motion. But this is not oscillatory motion or oscillatory motion. So we can say all simple harmonic motion, or all oscillatory motion or vibratory motion are periodic motion. But all periodic motion are not vibratory motion or oscillatory motion. Is it clear?
Yes, sir.
Yes, sir.
Because spinning of the earth periodic motion, but that's not oscillatory motion. But all oscillatory motions are periodic motion. Remember that. Okay, write down. So what is oscillatory motion, vibration motion? Write down. It is that motion in which a body moves to and fro. It is that motion in which a body moves to and fro. A body moves to and fro. You understood the meaning of to and fro? To and fro.
Yes,
Yes,
sir.
And back and forth. Back and forth. Back and forth. Back and forth. Repeatedly. 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 In a definite interval of time. Repeatedly in a definite interval of time. In a definite interval of time. In such a motion, the body is confined. In such a motion, the body is confined within extreme limits. Within extreme limits. On either side of its mean position. On either side of its mean position. Thus, a periodic and bound motion of the body. Thus, a periodic and bound motion of the body about a fixed point. Periodic and bound motion of a body about a fixed point is called oscillatory motion. Is called oscillatory motion.
Sir, periodic and bound after that?
Periodic and bound motion of the body about a fixed point is called oscillatory motion. That's why I told you keep your note along with you so you can easily check with the note what you are writing. Look here.
About a fixed and
about a fixed point is called oscillatory motion.
thank
Look
you,
here.
sir.
It is that motion in which a body moves, look here, to and fro, back and forth, repeatedly in a definite interval of time. In such motion, body is confined within the extreme limit. See, this is the extreme limit. More than this, body will not go. Within the extreme limit. On either side of the mean position. This is the mean position. When it is at rest, where it comes, that's the mean position. Either side it goes, same distance. That's a periodic and bound. Periodic means within fixed interval of time. And bound motion of a body is called oscillatory motion. Is it clear?
Yes,
Yes,
sir.
sir.
Next one. All periodic motion are not a simple harmonic motion. All periodic motion are not a simple harmonic motion. But simple harmonic motion are periodic. But all simple harmonic motion are periodic. What is your doubt, Mas? Mas, you have any doubt? Okay. All periodic motion are not simple harmonic, but all simple harmonic motions are periodic motion. And what is a simple harmonic? What is the meaning of this simple harmonic? What is the meaning of this harmonic? Look here. In maths, in mathematics, there are two functions you might have studied, sine theta and cos theta. Sine function and cos function. These functions are known as harmonic functions. Why do we call it harmonic function? We know value of sine 0, 0, sine 91, sine 180 minus 0, sine 270 minus 1, sine 360, again 0. If you plot a graph, okay, this is 0, this is plus 1, this is minus 1. Okay, this is 0, 90, 180, 270, 360. We are plotting a graph. So when 90 degree comes, we can say it has a maximum value 1. 180 degree, sine has a 0 value. Then again 270 degree, again 1. 360, again 0. Again it will repeat. Your total phase difference is 2 pi radians, isn't it? 2 pi phase difference. You know this meaning, right? 2 pi means 360. It comes in 90, 180, 270, 360. So 2 pi, 360 it covers. You have idea about it, right?
Yes, sir.
Yes, sir.
So every 2 pi radians, this will repeat. These kind of functions, cos also. Cos means same thing, but it will start from here. You see, first is 0, cos 0, 1, cos 90, 0, cos 180 minus 1, cos 270, 0. This 360. Only difference, when sine is starting from 0, other is starting from 1. This is only difference. Clear? So here for simple pendulum also, if you are taking, see, this is 0 times 0. It goes to plus value, plus 1. Come back to 0, minus value, again 0. So this and this sine functions are similar. That's why this motion of simple harmonic motion. So any such motion which we can express in terms of sine theta and cos theta, we can call harmonic functions. Is it clear?
Yes, sir.
No. In that, simple sine functions are known as sine and cos. So we call it simple harmonic functions. Right now. Out of all trigonometric functions, out of all trigonometric functions, only sine and cosine, are simple periodic, as well as bound, These functions have a periodic change of 2 pi. These functions have a periodic change of 2 pi radians. These functions have a periodic change of 2 pi radians and are called harmonic functions. Here the oscillatory motion can be expressed. Here the oscillatory motion can be expressed. Here the oscillatory motion can be expressed in terms of these harmonic functions. And are called simple harmonic motion.
In terms of?
Here the oscillatory motion can be expressed in terms of these harmonic functions. I told you simple pendulum. This can be expressed in terms of these harmonic functions and are called simple harmonic motion. I will show you how we are going to express this motion of simple pendulum in sine and cos. Next heading, you write simple harmonic motion. Simple harmonic motion. Without this chapter, 12th standard, you are not going to understand even one word. Those who are absent, I don't know how they are going to manage. They may have tuitions or big people. I don't know. Simple harmonic functions. Simple harmonic motion. Simple harmonic motion. Direct, right now. A type of periodic motion. Simple harmonic motion. It is a type of periodic motion in which, there's a definition, simple harmonic motion. A type of periodic motion in which particles moves to and fro and back and forth, to and fro and back and forth, repeatedly,
In which, after that?
in which a particle move to and fro and back and forth, repeatedly, about a mean position, under a restoring force, about a mean position under a restoring force, which is always directed towards the mean position, which is always directed towards a mean position. I will explain.
About the position.
Repeatedly about the mean position under a restoring force, which is always directed towards the mean position, and its magnitude at any instant is directly proportional to the displacement of the particle, from mean position at that instant. Displacement of the particle from mean position at that instant.
Sir, is directly proportional to?
The displacement of the particle from mean position at that instant. It means, suppose here we are taking a spring. Okay, we are taking a spring. If this spring I am stretching from here, see this position I'm stretching, we know this spring will develop a restoring force Kx, isn't it? Tell
Yes,
me.
sir.
From here, if I release, it will come back to this place. But due to inertia, it will not stop there. That will go to just the same distance, opposite side. So X again. Again, restoring force will develop. So when this is going out and out, how much outward it's going, that much restoring force will develop. So restoring force is directly proportional to X. But this restoring force acting opposite to the displacement. Displacement is outward, restoring force is inward. Any doubt?
No, sir.
Similarly, once it's moving this side, see, displacement is outward, restoring force is inward. So restoring force is always towards mean position. That means if it is going outward, restoring force will pull it center. If it is going inward, again, restoring force will pull it center. So restoring force is always directly proportional to displacement. X or Y, anything you can take. X or Y. Proportional, but minus sign. Minus sign indicate restoring force always opposite to displacement. Is it clear?
Yes, sir.
Yes, sir.
So that's a statement they say. Okay, now continue. Then mathematically, F is proportional to minus Y. Here spring, this way they are taking. See, one spring, we are pulling down. So spring oscillating here and oscillating here. If it is coming down, the restoring force will be upward. If it is going up, restoring force will be downward. Okay, more displacement if we go, more restoring force will develop. Then only it can come back to its original place. So F is directly proportional to minus Y. And F is equal to minus Ky, where K is spring constant, where K is spring constant or force constant, where K is called spring constant or force constant. Negative sign indicate the restoring force is always towards mean position. Negative sign indicates restoring force is always towards mean position and opposite to the displacement. and opposite to the displacement.
Sir, can you repeat it again?
Negative sign indicate that the restoring force is always towards mean position and opposite to the displacement. Next one, geometrical interpretation. Geometrical interpretation of simple harmonic motion. Geometrical interpretation of simple harmonic motion. By this method, we are going to develop the formulas which explains the motion of simple pendulum, spring system, all vibrating system. We are going to explain in some formulas. Geometrical interpretation of simple harmonic motion. Look here. Here, let us imagine a particle is moving along the circumference of a circle. This is its y-axis. This is its x-axis. Okay, a particle is moving along the circumference with a constant speed. Initially, time particle is here. After some time, this particle will reach, that is t is equal to t by 4. Then the particle will reach here, that is t is equal to t by 2. Here when the particle reaching t is equal to 3t by 4, here t is equal to t again. Any doubt?
No, sir.
No, sir.
Angular speed of this particle is omega. Omega means 2 pi by t. This formula, you know that, right? Total angle by total time. Angular displacement by total time, isn't it? For one complete revolution, 2 pi radians is theta. Time, 1 period. That is 2 pi by t. But omega is equal to, see, theta by t. Theta is equal to omega t. Any doubt in this?
No, sir.
Now theta is equal, omega is 2 pi by t. Okay, this formula we know. This t we substitute. When t is equal to 0, theta 0, this point. When 2 pi by t, this t is equal to t by 4, we substitute here. T by 4. Then you will get answer pi by 2. If you are substituting t by 2 here for t, then you will get 180 answer. Pi answer will come. If you are substituting 3t by 4 for the time of t, then you will get 270 or 3 pi by 2. If you are substituting t here as a t, then you will get 2 pi. This is what you're going to get. I think you understood how to use this formula. Theta is equal to omega t. Angle keep on changing. Omega is constant. T value keep changing. So theta changing. Any doubt in that? Please tell me.
No, sir.
Everyone is clear, right? That mathematical part. Omega
Yes,
constant.
sir. Yes,
T
sir.
0, you can see 2 pi by t into 0. If you are putting, answer will come 0. Okay. Similarly, 2 pi by t, t by 4 you have substituting, answer will come pi by 2. That means 90. This value if you substitute, you will get 180. This value if you substitute, 270. This is 360. Like that, answers will come. Okay. Now look. Here I am introducing a term which is called projection. You see, projection. From this here, this is the radius of this one. Okay, radius. That I am marking as A or R. Anything you can give. Here I am marking A. This is the particle P. So radius of this circle is A. Okay. Now from here I am marking a projection. You see, here to here I am marking a projection. Projection means a perpendicular drawn to y-axis or x-axis. Okay, it can mark to x-axis also, no problem. It can mark to x-axis. Now you see, from center to this point M, this distance we call y. This distance we call x. This is n. So O to M, that is y. O to n, that is x. Any doubt?
No, sir.
No. Now look here. This p value. Look here what's happening here. Okay. Look. This OP. I'm turning it. See now, it is changing. Now you see this dotted line, how it went, this dotted line. X value decrease, right? Can you see that? Can you see some dotted line over there?
Yes, sir. Yes. Yes.
So X value decreased, Y value increased. Okay, here see X value 0, Y value maximum. Okay. That projection went, see, When I kept here, you see, projection was on this yellow line. See that dotted line along the yellow line, along PM and PN, that lines were, right?
Yes, sir.
When this is moving, you see what's happening here. When this is moving, that dotted line is shifting. Can you see?
Yes, sir.
Yes,
Now
sir.
here y value maximum, x value 0, right?
Yes, sir.
Yes, sir.
Again, it is going down. You see? Now projection is changing. Look here that now. This point you see now, y value decreasing, x value increasing. Now you see y x is maximum, y becomes 0, right?
Yes, sir.
Yes, sir.
Now again you see it's going opposite side. See y value increasing, okay? X value decreasing. Here y value maximum, x value 0. Again it is going, you see, y value decreasing, x value increasing. That means when this is rotating all around, when this arrow rotating, y value will increase, x value will decrease. When y value decreasing, x value increase. Here we are going to study only y value, x value we will study later. Okay. So now when P is rotating along the circumference, this projection MP keep moving up and down. You understood?
Yes, sir.
Yes, sir.
Look only y-axis. I'm telling you, see here I am marking P. Look PM, that's a projection. When I'm moving it, projection went up and again projection come down. You see that y value come down and y value going to opposite side. Again, it's coming to 0. Only y value check. So each time it's revolution, that projection makes simple harmonic motion. To and fro, back and forth within a fixed interval of time. So particle P making a circular motion, but projection making a simple harmonic motion. So here we are going to study the motion of that projection. Here we are not going to study motion of the particle. We are going to study when particle P moving along the circumference, what is the projection happens. Is it clear?
Yes, sir.
Now to understand this, 2-3 videos I will send to you. Compulsory you must watch. Just after receiving 5 minutes rest, you just watch it. It's very interesting idea you will get. Okay,
Okay, sir.
Because that I cannot show here now, no time. See, actually they show a circle moving like this. When the circle is turning like this, clearly you will see this projection is going up and down. Very interesting explanation. Once you understood, subject is interesting.
Sir, the video yesterday you sent that video.
It's already sent to you. Have you seen?
Yes,
Along
sir.
the circle it's moving. Have you seen that?
Sir, I didn't
Anyway,
open the video.
I'll check it.
No,
If I
sir,
have
you
sent,
did
we'll
not
check it
send, sir.
again.
You didn't
Anyway,
send.
look here now. So this projection we are studying. Now look, this is theta. This is also theta. This is equal to omega t. Theta is omega t. Okay. Now look at this here. Sine theta is equal to, sine theta is equal to opposite side y. Hypotenuse A. So y is equal to a sine theta or y is equal to a sine omega t. So now we got the formula. This is the formula which represents every simple harmonic motion. Say for example, here you see T0, substitute here T0, y is equal to 0. T by 4 is substitute. Omega t will come 90. Then you can see y is equal to a. This a will be maximum value. Now y is equal, this is 180 substitute, again y value 0. Here 270 substitute, y value come opposite. So without diagram now we can explain this one. So this is called geometrical interpretation. With the geometry, we are interpreting simple harmonic motion. Now this formula we are bringing to the real situation of the life. For example, a simple pendulum. Time 0. We know this simple pendulum go to this side in a time t by 4. This displacement we call y is equal to amplitude. Maximum displacement it goes, we call amplitude. Here maximum displacement we call amplitude. Now it come back in a time t by 2, isn't it? Then it goes to opposite side. This is 3t by 4. This is t and it repeat. Same way like this. So this diagram and this motion and this equation we all can connect. See here T0. T0 means this pendulum is here. This point. Everyone understand now. T by 4. That means oscillation reached up to here. So we can say omega T 90. See, here it is 90. Isn't it? That means Y value maximum. Here Y value maximum. Now, when you're coming to real situation, you should not ask me where is 90 angle. It's not this angle. This is not this angle they are speaking about. They are interpreting with this diagram, this motion. This vibrational state is known as phase. This is very, very important information, phase. So phase is 90 degree means particle is extreme position. That means T by 4 time of oscillation starting. Now T by 2. This is 180 will come. See, this reaching here, Y value 0. So T by 2 means you should know this is 180 degree. Displacement is 0, but going opposite side. 270, this position. 360, this position. So motion of this simple pendulum, we can explain this formula. So now this is a simple harmonic motion because this motion we explained in terms of sine. With the cos also you can explain. If you study X, you see, this is theta. Cos theta is equal to adjacent side X divided by A, hypotenuse. X is equal to A cos theta.